Hello, meteorology students. Welcome back. This is the second part of week three's video. Today, we will go over air temperature data, daily temperature, use of temperature data, the air temperature and human comfort. We'll also go over measuring air temperature. And then at the end, I kind of like to include something that I did actually in undergrad relating to weather and art. So let's get started. All right, for the first thing we have here is the diurnal temperature distribution above the ground. Diurnal meaning during the day. So you can see we already started in the last, I want to say the first slide or the first video that we are warmer at the surface than we are aloft during the day. And at the night, we're cooler at the surface than we are aloft. So we kind of, but that doesn't, it changes. Like it's not consistently the same, change between the surface and aloft. It changes throughout the day. So we kind of have a representation here of that with the temperature on the bottom and the altitude here on the side. You can see that we have a nice little temperature inversion here in the blue line. This is 5 a.m. So we would expect there to be somewhat of a temperature inversion. The sun isn't up yet. And then at 8 a.m. we see more of a vertical line. There really isn't that much of a slope to it. At 10 a.m. we start seeing a slope. It's going to be about 90 here at the surface, and then it'll get, cooler as you go up. And then we have actually at noon we have quite a bit of a slope here. This is going to be the highest amount of incoming radiation during that time frame. So we're really going to have a lot of warming here at the surface. There's going to be a large difference between the surface temperature and the temperature, just a few meters up here. And then it starts subsiding again at 3 p.m. There's going to be less of a slope, and then at 9 p.m. you'll go back to where there's that inversion because the sun went down. So remember, this kind of is determined by the amount of incoming solar radiation, not necessarily the temperature throughout the atmosphere, because it does take a little while for that atmosphere to warm, up here. So the warmer part of the day will be still 3 or 4 o'clock, but right down at the surface, it's actually warmest right around noon, because that's when the most amount of solar radiation is hitting the Earth. This kind of is a nice little also representation we have about the day and night temperature change. So the distribution basically between the temperature changes. So you can see, here's our daytime temperatures, here's our nighttime temperatures. This is going to be like ground floor or bottom of this building, and then we're going to go up in altitude or feet, it's on 980 feet up here or 300 meters, at the top of the building. And you can see that there's a daily range of 8 degrees here at the bottom of the building, but at the top of the building is actually 4 degrees. So there really isn't as much of a daily change, higher up than there is, right down at the surface. So, that brings us to, how we use temperature and how we decide, how we use temperature, I'm sorry. So one of the ways that people actually use temperatures is by determining, the utility companies will determine when we start using more energy. So we have things called the heating degree days and the cooling degree days. These days is what PG&E will use to determine how much energy they think that we'll use. So, basically heating degree day is based on the assumption that people will use their heaters when temperatures drop below 65 degrees. It's calculated by subtracting the average temperature for the day from 65. And a cooling degree day is pretty much exactly the opposite, except for we'll start using air conditioning once it goes above 65 degrees. So they'll look at these two things to determine when we'll be using our air conditioning and also when we'll be turning on our heat. I know that there was in New York, it got really, really hot a couple of years ago. I remember that they were really, really struggling keeping the grid going because so many people were using electricity and they started having power outages, based on, the energy usage. And this kind of shows you how many, heating degree days there really can be on average, depending on where you live. It makes sense that we would have, Florida having the highest amount because, people will be using the air conditioning more, down there throughout the whole year, where you can see how there's kind of an area here where the valley is, and then it tapers off. So, California is kind of an anomaly like that, because if you see how like the it goes down basically, like, in the desert, it kind of goes, there's kind of a clear line here through Kansas and Missouri, and these areas right here. So a lot of these areas in the middle here where this gradient is pretty rough, this area right here they can determine pretty, somewhat easily, but like over in this area is going to be kind of more iffy really as to what each day brings as far as, the weather. And this is going to be the same exact thing, but cooling degree days. So you can actually see the opposite going on here. They're going to have less of these days down in Florida and more of them, up here in the north. Again, we're going to kind of have a little bit of an anomaly here in the Central Valley. Kind of interesting how you can see that kind of sticking out. And a lot of these weather maps, you can kind of see how California kind of sticks out like as an anomaly for these types of things. I know my apartment doesn't have air conditioning because I don't really need air conditioning. So, and that's kind of weird to me because I've never lived anywhere that didn't have air conditioning. And I got the cooling degree days here. I kind of put this up as far as Lincoln, Nebraska, because, the first time I taught this class, or maybe the second time, they were having a really, really unusually cold winter, I think it was. So it kind of, was to show that. And then we get to basically how farmers will use it. So there's a thing called a growing degree day, and this is going to be a guide so they know when to plant and also when to harvest their crops. I know some people that even have what do you call it, gardens, and my father has this huge crazy garden in his backyard. He'll actually use growing degree days so he knows when to plant certain things and when to expect to be able to start eating the things that he grows. But it's pretty interesting how they do that. There's actually going to be a base temperature for each crop here, so you can see how like sweet corn would be, and corn, soybeans is kind of popular in Nebraska. So the base temperature is going to be 50 degrees. So if you take basically, the mean temperature, it might be 80 degrees. So you take that 80 degrees minus that, base temperature of 50. So then that would be 30 growing degrees days. And then once it hits, total of 220, then they're going to know that that's usually when the crop is ready to be harvested. Kind of interesting too, because if you have, I know last year it got warm really fast. And so the growing degree days accumulated earlier in the year than it normally did. So the crops were getting more ready faster than they normally do. So, and maturing faster as well. So it kind of threw off a couple other things, like there, typically areas that would flood and certain things like that. So kind of interesting how that can vary year to year. And when they have an exceptionally different year than another year, how, it'll accumulate really fast or really slow, and they could potentially have freezing going on and things like that. So, okay, and then we also have something called the wind chill index. This is something that, well, you guys would not know very much about unless you're from an area where there's a wind chill. But basically a wind chill is going to be a combination between the temperature and the wind speed. So if you take the two and you kind of put it into this chart here, it's kind of interesting. If the temperature, say, is like -10, commonly gets that in Nebraska, and the wind is, say, 15 miles per hour, that's not very windy. You're looking at it feeling like -32 degrees. That's cold. And if you see these shades here, this is going to be frostbite time. So, if it's -32 degrees in 30 minutes, you could potentially have frostbite. That's not very long. You could go sledding per se for a couple hours. And if you're not properly taking care of yourself, you could easily, run into some problems. But these 5-minute temperatures, these are where it really, really gets super, super dangerous. We don't want anybody really working outside or kids walking to school or anything like that, because they're really at risk of getting hurt by this frostbite. You might be asking yourself, what in the world is frostbite? Well, this is what frostbite looks like. It's very serious. Being out in the cold, not only can you die from hypothermia, but before hypothermia kicks in, you can have freezing skin. Basically, that's what happens. Your skin freezes, and that's called frostbite. It usually happens in your hands or your feet. It's the closest away from, your body core where it's warmest. So these things are dangerous because you can lose your limbs and all sorts of other things can start happening, after you develop frostbite. Okay, so how do we take measurements of temperature? Right, there's different types of temperatures thermometers that we might have. Basically, daily temperatures are measured at automated weather stations at the National Weather Service, and they call those AWS. The sensors, might include the electrical resistance thermometer. That's what the AWS uses. Basically, it takes the temperature and specific, and then it automatically just basically shoots it into the computer inside of the office, so they don't have to go outside and actually physically look at the thermometer. You might have the I can't say every word, thermistors, which is where the radiosonde is attached to the weather balloon. That's what they use for those. And then thermocouples. So there's a few different types, and they use them for different types of, readings and depending on how they're using it, what they're using it for. But the main thing, as far as like the National Weather Service, they have a couple instruments outside of each office, and this housing or encasing here. Actually, I saw one. There's just some places you can go where they're like studying science actually and studying weather, and you can find them there as well. I found one time in Nevada when I was driving around. But this is basically what it's going to look like. The first thing you might notice is it's inside of a shelter, and that's on purpose because you don't really want to be measuring the amount of radiation hitting that thermometer. You want to be hitting the actual air temperature, and that's what you want to be measuring. So the only correct way to do that is actually in the shade. The other thing is it's not on the ground, and you guys could probably already guess this now, is because it's way cooler and way warmer at the ground than it is just a little bit above the ground. So we don't want it to be on the ground. We want it about, 1 meter up, 1.5 meter up, about, 5 feet or so. We also want it away from buildings. That is due to the fact that, buildings actually will absorb more solar radiation, and they can actually be warmer than, certain other things. We don't want them on cement or any type of asphalt because that would be black, and, the albedo is lower, so it would absorb more energy. So we want it to, this is a perfect place type of idea where you would want it. Somewhere, on a ground in a field, something with a very neutral albedo. We want it off the ground, when it in the shelter, in the shade. Let's see, make sure I hit everything up here. Yeah, so that's generally speaking, the standards of where, they might take it. So, if you've ever like driven by, I don't know, some sort of building that might have a temperature, on top of it or, on the side of it, and it's like, 200 degrees or something, the reason why is those standards aren't being adhered to. It might be on a roof, it might be, somewhere where, or directly on the ground, it might be in different places that just aren't, the correct way to do it. Another interesting thing is if you're in your car and your car takes the temperature, it can depend on the color of your car as to whether it's reading a little bit warmer, a little bit cooler, because of that albedo, and whether it's absorbing more solar radiation or reflecting more, that kind of thing. So, the National Weather Service is pretty good at making sure that these are adhered to. The rest of them that private companies do, that's where you'll start seeing these wonky type of measurements out there that, don't really make any sense. Okay, so here's the group questions that I do for my live class. You guys can pause here and try to answer these questions. I'm going to just move along though here. Okay, so this is kind of where I kind of like to talk about the intersection between art and science. When I was in undergrad, I was asked to be part of a project, and basically it was done by an artist in Omaha. He was an intern there at the Bemis Center for Contemporary Arts, and after he had graduated, he decided to come back and kind of give back to where he interned at, and wanted to build a rainbow over the Bemis building. Now, the Bemis building is this big building. It's like, I don't know, 5 stories, 8 stories high, something like that. And so, and they wanted to collect rainwater off the top of the building, and then they brought the water down into these big barrels and stored it there, and then cleaned the water and pumped it back up through the building, and then shot the water about 250 feet up off the top of the building. So our job was to figure out the climatology, how much rain we would potentially get, and how much we would need for the rainbow or have for the rainbow and be able to store, and also the vantage points, because a rainbow is an optical illusion and the sun has to be 45 degrees behind you. The sun isn't always in the same place all the time, depending on what where it is in the season. And they did this all summer long. They were supposed to do it in the morning and in the evening, but they ended up only doing it in the evening because, the water ended up like in the morning going on people's cars and they didn't like it. So we ended up just doing it in the evening. So when I was part of this project, I just kind of took a few pictures. So here's kind of what the nozzles look like. There was 6 of them, 3 on each side of the building, because what they could do then is recollect some of this water. They would shoot the rainbow whichever direction the wind was moving, then they would do the nozzles on the other side of the building, so that it would the water would go over the building, and then they'd be able to recollect that water and use it again for another rainbow. So this is the First National Building. This is a Woodman Tower. This is downtown Omaha. This is about it, guys. I mean, that's the huge city right there. This is the weather station that we had. So this is kind of an idea of the 3 of them that, 1, 2, 3. For any of you guys who might be interested, Omaha is right next to Iowa. The Missouri River is right in the middle. So that's Iowa right there. And this is Nebraska. Okay, this is the building. Okay, how many stories did I say it was? 1, 2, 3, 4, 5. So it's 5 stories tall, this building. And here's our storage units that we had. And I'm sorry if you guys can hear that. I think my neighbor's vacuuming. Okay, and then you can see how they were able to then, bring the rainwater down. It just came down off the gutter right here and into it. And then it came from the gutter on the other side through the building and then down into this one. And then there was another, see this one right here? It came into this one temporarily before they did it, and then cleaned it. Cleaned the water before they pumped it back. This thing right here is the thing that pumped it up. Now, this is just a size comparison. I don't even know who this guy is. He just happened to be standing there when I took the picture. So just to kind of show you guys how big it really is here. These are the cars. These are the ones that the guys didn't like it in the morning, getting their cars all dirty. And this is kind of it going through, like a picture of it going through the building. This is one of my favorite pictures I took. This is actually the artist, Michael Jones McKean, and this is the look on his face. The first day that we did it, it was like the trial run before we actually did it for the public, and he was just super excited when we actually were seeing a rainbow and it actually worked. And here's this huge rainbow over our building. And this is what it looked like. You can see the nozzles here and how they were shooting up the water, and how the rainbow has appeared here. See how it's a clear sky. There's no clouds. So, I kind of like to show my students this because I feel like, I hear a lot of people telling me that, they're not really into science, or, they might have kind of a negative idea of science, and that maybe they're more into art, maybe they're more into, something else. And, I kind of feel there's definitely an intersection between art and science, and that line between the two is definitely graying, because, when I went into atmospheric science, I never thought I'd be part of an art project. I mean, I can't draw. I'm like horrible at art, but I actually was part of an art project, and I'm excited to be part of that. So just to kind of show you guys that, you may get involved in something else, that has something to do with science, even if you're into art. And that's the end of my slideshow. So I hope you guys have a great week. And if you have any questions, email me, and I'll see you next week. Thanks.